Welcome back. So I have a square table here, and in each corner of the table, I have a pulley. And so around these pulleys, you have this wire, and so from here, some kind of force is applied. Let's call this force P. And so essentially you have this middle line here, you have 30 degrees here, and also 30 degrees here. Basically, if you look at this table from the top, then these are your pulleys. This is the wire. Someone applies a force in this direction with the force P. And so you have 30 degrees here and 30 degrees here. Let's call these pulleys like this: A, B, C, and D. And now, each pulley can withstand maximum 120 newtons. So if one of these pulleys experience more force than 120 newtons, then that pulley will break. And so your task now is to calculate the maximum force P that you can apply here before one of the pulleys breaks. So try to figure that out by yourself. What's the maximum P that you can have before breaking one of the pulleys? And when you're done, then the solutions are in the next video. Thank you very much. Welcome back. So let's now figure out our P max that we can have before one of the pulleys breaks. Remember, a pulley will break when it experiences more force than 120 newtons. And so maybe a good idea to get started is to disassemble the system. So let's call this corner here E. And so I have this point E here, then I have this force P, then I have a force in this direction and in this direction. That's force ED, and that's the force EA. And so I have pulley A here, pulley D here, then pulley B here, and pulley C. And so because of this wire, and because of the Newton's third law, I will have this force here, then this force here, then this force here, the same one here, and then also I have it here, over here, and here. Essentially what I have done, I have mentally cut the wire here, then also here, then here, and here. And because of the fact that you don't have acceleration anywhere, and you have a wire here, in these cutting points, you always have the same forces. So for example, here I have FAB, here FBC, here FCD, but they are all equal because you have a cable, and in this configuration, together with the pulleys, the cables transmit the internal forces, and therefore whether you cut the cable here or here or here or here or here, you will still have the same magnitude on one side and on another side. So just to be clear that all these forces are equal to each other. That's because the cable transmits the forces like that. And then the reason why this force and this force have the same magnitude and they're opposite in direction, that's because of the Newton's third law. Therefore, what I will do, I will simply call all these forces F. And don't forget, you have 30 degrees here and 30 degrees here. When you mentally cut your wire, then you have to have these opposite forces here. Because in reality, you haven't cut the wire. In reality, the wire is at rest. So something needs to keep this wire together. And it's this force if you cut it in this place. However, here it is said that the maximum force a pulley can withstand is 120 newtons. Let's first take this pulley B. Let it be here. So this pulley experiences a force in this direction and the same force in this direction. So you're pulling this pulley down and to the right. That means that the resultant force that this pulley experiences is this one here. And since both of these forces are equal, then that means that here you have 45 degrees. So that's the resultant force that this pulley B experiences. And then pulley C, it experiences the same resultant force. So pulleys B and C, they are in the same situation. What about pulleys A and D? Well, if we use the parallelogram rule, then this would be the resultant vector that pulley A would experience. You just draw one line parallel to this vector, and then one line parallel to this vector, and this is your resultant vector. So here, in order to specify, I'm going to write here FRB, and here let it be FRA. So the pulleys A and D, they also experience the same resultant force. However, you can clearly see that pulleys B and C experience a greater resultant force, because in case of all the four pulleys, you have this red force vector in one direction and in another direction. So this F is equal everywhere. But if you compare pulley A and B, then first of all, since you have 30 degrees here, that means that you also have 30 degrees here, so that will clearly give you a smaller resultant force than in this case where you have 90 degrees here. You can imagine that if you have some kind of pulley and you have a force vector in this direction and then also in this direction, then your resultant vector would be 0 newtons. If you have this situation, then this is your resultant vector. If you have this situation, then you have this resultant vector. Obviously it's bigger. And then, if you have this situation, well then your resultant vector is even bigger. It's this one here. And if you have this situation, then this would be your resultant vector. It would be the biggest case. This resultant vector would be twice as big as this red F vector. So it would be 2 times F, because you would just add up these two vectors that point in the same direction. However, that's not the case right now. Right now we have two cases, this one and this one. And so in this configuration, pulleys B and C experience the greatest resultant force. And now you know that the maximum resultant force that a pulley could withstand was 120 newtons. And so how would you calculate this FRB that you have here, or FRC? Well, since you have a right triangle here, you can say that FRB, which equals to FRC, well, it's simply square root of F squared plus F squared. And that will give you square root 2 times F squared. In other words, you will have square root of 2 times F. And so if we say that this is max and this is max, what they can withstand, then this thing here, it needs to equal 120 newtons. Again, the reason why we're not considering pulleys A and D is because here the resultant forces are smaller than in case of B and C. If I say that FRA equals 120 newtons, which would also be FRD, if I allow these two resultant forces to be 120 newtons, then these two resultant forces, in case of B and C, will be greater than 120 newtons. and then these pulleys will break. That's why I only allow these two resultant forces to be 120 newtons. And so that means that this force F, the red one, which is this one here, I can say that it equals 120 divided by square root of 2. And that will give me 60 times square root of 2 newtons. So I now know my force F, and it's this value everywhere. Here, 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 also here, and here. And so now, if I construct this free body diagram, positive x is here, positive y is here, and I'm going to do it for point E, so this one here. So I have this force P, and then I have this force F, and the same one here. And so since I have 30 degrees here, I know that I have 60 degrees here, and also here. And now I only need to apply the equilibrium principle in the y direction. If this is my maximum resultant force, then this is my maximum force that I can have here and here. And now I need to find my P max, and according to this equilibrium principle, I will have minus P max plus 2 times F max times sine 60 degrees, and that must be 0, which means that my P max, it equals 2 times 60 times square root of 2. This is your F max times sine 60 degrees, and that gives you 147 newtons. And that's it. You can only apply maximum of 147 newtons here and not more, because if you apply more, then the resultant force in the pulleys B and C will be greater than 120 newtons, and they will break. And so here I have created a Python animation for you to show you what kind of resultant force a pulley would experience when it has these two forces but in different directions relative to each other. So both of them are 200 newtons, and the red one, it's static, so it's not gonna move. But the blue vector will move around the pulley. So you can see that as this blue vector goes along the pulley, your resultant vector here gets bigger and bigger, and so now it gets even bigger, and when it becomes parallel to the red one, then it's gonna be 2 times greater. It's gonna be 400 newtons. And then here again, it's gonna start decreasing and decreasing, and that's how it goes. And now you can see that when they become opposite to each other, the red and then the blue vector, then the resultant vector becomes 0, like this. So for example, this case here, it was very similar to this case in case of pulleys A and D. And then when your blue vector becomes perpendicular to your red vector, then the resultant vector is now greater, and essentially this case, it's very similar to these two cases, pulleys B and C. In order to calculate the resultant vector, then it's even better to put your red and blue force vectors in the middle of the pulley, and so you can see that as this blue vector rotates with respect to the red vector, your resultant vector changes like you see here in the animation. Here it's maximum, and then here again it starts decreasing because the directions of the red and blue vectors, they become further apart from each other. So this case is what we had with pulley B and C, and this one is with pulleys A and D. So that's how it is. And now you can see that your resultant vector is 0 because the red and blue vectors are opposite to each other. So that's how you solve this exercise. Thank you very much. Welcome back. So I have this pulley mechanism here. So here you have the wall, and then you have a cable that goes around this pulley, then around this pulley, and then around this one here, and then you have a box here. The mass of this box is 10 kilograms. We neglect the size of the pulley, and now this pulley here, let's call it pulley A, it can actually move. So this one cannot move, this one cannot move, but pulley A can move, for example, in this direction. And it would move because of this box. And so I have another wire here, and let's call the tip of this wire B. And now, if I want to have 45 degrees here and 75 degrees here, then how strongly do I need to pull this wire, and also at which angle theta? So I have the mass of the box, I have the angles, and my two unknowns are FAB and theta. What should they be in order to keep the system in equilibrium in this state with these angles? So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this problem. Let's find FAB and theta in order to keep the system in equilibrium in this state with these angles. First things first, this box has a mass, so its force of gravity is 10g. And you already know that if I mentally cut the wire here, then of course in reality this box still stays at rest, and that only happens because you have 10g here and 10g here. These two forces in the opposite direction, they don't let this box to fall down. Similarly, if I mentally cut it here, then because of the fact that it's a wire, this 10g force gets transmitted here and also here. And then if I perform this mental cut here, then again, I will have 10g here and 10g here. And also if I do it here, then you have 10g here and 10g here. So as you can see, it is very convenient to mentally cut these wires for force analysis. Because if you mentally cut a wire, but in reality the wire is not cut, so the structure doesn't break, therefore you know, thanks to Newton's third law, which forces you have here. Especially if you have a wire that transmits forces so conveniently. So you have 10g here, and because of that, you already know that 10g is also applied to this point on the wall as well. And now, even though this wire does not really go through this point A, but if we neglect the size of the pulley, if we just assume that the pulley is very small compared to everything else that we have here, then we can still construct a free body diagram for this point A. So again, this is your positive x-axis, positive y-axis, and so this is point A. And now from here you can see that you have 10g in this direction, you have 45 degrees here, then you have 10g in this direction, so you have 75 degrees here, and now you have this force FAB and this angle theta required to keep this entire system in equilibrium. And so again, we use our equilibrium principles. First of all, we have the sum of the forces in the x direction must be 0, so I will have FAB times cosine theta minus 10g times cosine 75 degrees. With that, I obtain the horizontal component of this force, and then minus 10g cosine 45 degrees. That's the horizontal component of this force, and that equals 0. And then the sum of the forces in the y direction must also be 0, so I will have minus FAB times sine theta plus 10g times sine 75 degrees minus 10g times sine 45 degrees, and that must be 0. So now I obtain the vertical components of these three vectors. So I start with the first equation. In general, we have two equations and two unknowns, FAB and theta. But if I take the first equation, then I can express FAB like this: 10g over cosine theta, and then cosine 75 degrees plus cosine 45 degrees. And then I can take the second equation and I can rewrite it like this: FAB times sine theta, which is this term here, it equals 10g times sine 75 degrees minus sine 45 degrees. So I simply took this term and I put it to the other side of the equation sign, and then I factored out these 10g's. And so why did I put it in this form? Well, now I can take this FAB and I can replace it with this one here. If I do that, then I will have this one, which is this side, equals this one, which is this side here. And now right away, I can get rid of 10g here and 10g here. And also this one here, it will be tangent theta. So I can rewrite my tangent theta like this. This is the numerator and this is the denominator. If you calculate it, you will get 2 minus square root of 3. And so theta equals inverse tangent and then this number here, and that will give you 15 degrees. And so now you can take this equation and you can put 15 degrees into this theta here. So you will have FAB equals 10g over cosine 15 degrees times this one, and if you calculate it, then you will have 98.1 newtons. And there you go. This FAB needs to be 98.1 newtons, theta needs to be 15 degrees, and then this structure will be kept in equilibrium with these angles. Thank you very much. Welcome back. So I have a structure of cables here, and I have a cylindrical block here. Its mass is 30 kilograms, and so you have 60 degrees here, and the direction of this cable, B and D, it can be determined with this right triangle. And so the system is in equilibrium. And now the question is, what are the forces FBC in this cable, FBD in this cable, then FAB in this cable, and FAE in this cable? What are the magnitudes of these forces considering that this system is in equilibrium? Try it out yourself first and then see the solutions in the next video. Thank you very much. Welcome back. So let's now find these four forces. First of all, you know the mass of this cylinder. Therefore, you know that the force of gravity here is 30g, which means if I mentally cut this wire here, then I will have 30g here and also here. Another thing that we need to note is that the angle, which you have this one here, this is 60 degrees. That's because you have 60 degrees here. That comes from geometry. If I draw a straight line here, and then also a straight line here, then I have a rectangle here. So if I have 60 degrees here, I must have 60 degrees here. Because this cyan cable, this is like the diagonal through the rectangle. And so now let's draw two free body diagrams, one for point A and one for point B. Let's define our positive directions. And so let's start with point A. This is this point here. So you already know that you have 30 G's here, then you have FAE in this direction, and then FAB in this direction. And of course, you have 60 degrees here. So that's point A. And now here, I will have my point B. Due to Newton's third law, this force vector here is equal in magnitude to FAB and opposite in direction. Since it has the same magnitude, I'm just going to call it FAB because it's the magnitudes that we are looking for. Then I have this force vector, FBD, and this force vector, FBC. I have 60 degrees here, and then in here I have this right triangle to determine the direction of this force, FBD. And now we simply need to start applying our equilibrium principles. So let's start with point A. In the x direction, I have this equation here. In the y direction, I have this equation here. And now I can right away calculate my FAB, which is 30G over sine 60 degrees. And that gives me 340 newtons. And so I have 340 newtons here, and also here, thanks to the Newton's third law. And now I take my first equation and I calculate my FAE, which is FAB times cosine 60 degrees. I can replace FAB with this result, so I will have 30G and then this ratio, this cosine 60 degrees, it's this one here. This, of course, is 1 over tangent 60 degrees, and so that means that FAE equals 30G over tangent 60 degrees, and that's 170 newtons. And there you go, you have found your FAE. And now let's do it for the B point. In the x direction, you have this equation, so this 340 here, that's this one here. And so in the y direction, you have this equation, again this 340, it's this one here. And so right away, I can calculate FBD, and it equals this one, and that will give you 490.5 newtons. Instead of this 340, you can also write it out with this expression here. In that case, you can write FBD equals 30G over sine 60 degrees, which is this 340 here, times sine 60 degrees, which is this one here, times 5 over 3. And you can see that you can cancel out the signs here, so you will only have 30G times 5 over 3, like this, and that will equal 490.5 newtons. And now that we know our FBD, we can take this equation here, and so FBC equals this one here. This here, that's your FBD, and then this here, that's your FAB, this one here. And so if you calculate that, then you will have 562 newtons. And there you go. FBC equals 562 newtons and FBD equals 490.5 newtons. And that's how you calculate the tension forces in these cables. Thank you very much.